All right, let me go ahead and share so we can get started. We're gonna try to finish Alkenes today. Then I'll have to send you some videos for triple bonds. It's a little bit less. It's a little, there are fewer reactions, but we still gotta hit it. We won't get a chance to touch alkane stereochemistry, but we've already kind of seen a little bit of that, so we'll be good. All right, so we left off talking about Simmons Smith. We did oxymercuration, hydrochloration, and ozonolysis. So we're just gonna work through a few more examples. And yeah, I want to work through these. And this. And these. So we're gonna skip this reaction right here. That's a type of cleavage reaction, but we haven't talked about it, and I don't want to get into the weeds with that. So let's look at the next reaction right here. We have hydrogen gas, which is ECH2 like that. It's hydrogen gas in the presence of platinum oxide. Right, so platinum oxide is all of these types of reactions. You need a catalyst. So this is your catalyst. For that what type of reaction is that? If I'm adding hydrogen gas to an alkene.
Hydrogenation.
Say again.
Hydrogenation.
Hydrogenation. Good. What does it do to the alkene? If I'm alternating, I'm adding hydrogen, one hydrogen to each carbon in the alkene. All right, so I'll take that alkene down to an alkane. Right, so I'm able to take that alkene. So I turn the light off. There's litter. I see how you're looking at the board. So I take that alkene and turn it into. Actually work too. But they take the hydrogenation will take an alkene to an alkane. All right. Questions about that reaction? We've seen this multiple times now. So normally when you do a hydrogenation, it's either going to be in the presence of platinum or palladium as the catalyst. All right, let's go. We're going to go through this reaction wheel right here. Hopefully by now, you've taken my advice and made flashcards. If not, shame on you. All right, let's do, we're gonna go through this wheel, and each one of these has a reaction, right? So 1 to 2, 1 to 3, 1 to 4, 1 to 5, like that. So 1 is my starting material, which is here. Again, we're doing reactions of alkenes. So no other functional group matters. All we care about are the alkenes. So the carbonyls and all that stuff that you see as a part of this molecule, we don't care about that because the reactions that we're doing are specific to alkenes. So let's look at 1, 2, 2. Here. Right? What type of reaction is that? First of all, what happened? Going from 1 to 2.
The double bond is removed.
Double bond is gone, right? And there are no other functional groups there. I didn't add a halogen or an OH group or anything like that. So what must I have added to remove that double bond?
hydrogen,
Hydrogen. Good. So what set of reagents down here am I going to choose to complete that reaction?
H2 and platinum oxide. Oh, yeah, B.
Here. Right, these are conditions for ozonolysis. These are conditions for oxidation. And then this set of conditions is for that's specific to alkynes, which we'll talk about Wednesday. All right, so we can leave that. What about 1 to 3? What type of reaction is, you may not remember that one, but what happened in that reaction to the double bond? We talked about this Friday before we left for Thanksgiving, last Friday. No, Friday before that. Anybody? What did I do to the double bond? What does it look like I did to the double bond? I converted it into what we call a cyclopropane. I have a 3-member ring on that double bond now, or where that double bond was. So that is an example of, I'll give you this one. The Simmons-Smith reaction. Right, and just to give you a recap of that, we did that on Friday, where we take a alkene and convert it into a cyclopropane. And you use diiodomethane and zinc metal. All right, let's go to the next one. 1 to 4. What did I do there? What happens is the double bond still intact in the product? So the double bond is gone, right? But if you notice, where the double bond is up here is between these two carbons. Here and here. And the product, one of these carbons is here. The other one is here. And both of those carbons have been converted into carbonyls. So that's that reaction. I'm gonna give you this one too, because we only saw it once. Is ozonolysis. Right, in an ozonolysis, if I take a double bond, any double bond, let me just write this as a CH2. And I treat it with ozone and then zinc. Right, each carbon in that double bond is going to get converted into a carbonyl. It's an oxidation method for alkenes. Right, so that even though it's a ring, I can still crack that double bond in half. And if you're confused about the structure, right, let me do this. Let's put in a hydrogen here. All right, there's no hydrogen on the other side. So that hydrogen right there is here. And if we count the carbons in between, 1, 2, 3, 4, 5, 6 carbons, and this is 1, 2, 3, 4, 5, 6 carbons. Right, so the chain length is going to equal the ring length. Right, and this, since there's a substituent up here attached to the ring, we don't count that as a part of the backbone. All right, any questions about that reaction? All right, there's only one left, 1 to 5. What kind of reaction is that? What happened to the double bond? And when I ask that question, I'm asking, what's the product?
They became hydroxyl or alcohols.
Okay, so my product is a diol, right? And the alcohols are CN or cis, right? They're both going back into the board. So now let's look at the choices. What set of reagents do I have down here that can make a CN diol from an alkene?
D.
You say D? Good. Osmolation. That's exactly right. That's an osmolation. Right? It converts alkenes into diols. All right, any questions about the reactions depicted here? About any one of them? All right, let's go to the next part of the handout, which is here. Number 1 is just that question is dealing with the stoichiometry of hydroboration. So anytime you do hydroboration, the ratio of alkene to BH3 is always 3 to 1. Right, and that's because that BH3.
No, I'm sitting. That's what you're doing. Girl, stress. Yeah, me too. Girl, did they give you so much for the work, dude? One second.
All right. So the BH3, you can actually add three alkenes because you have three hydrides that you can transfer. So you can add three alkenes to that. So that's why the ratio is 3-to-1. Right, I think I showed you when we first started talking about this, part of the mechanism and why it's anti-Markovnikov, because you add B and H across the double bond to get that alkyl borane. So this question is just asking about that. So if I took this alkene and added it to BH3, if I added it once, I would get 8. There'll be 1 mole of alkene. Y'all following that? Because what I did here is I added one of the H's from BH3 to here. So I added H on one side, and then the BH2 is going to be on the other side of that alkene. I'm sorry, here. My bad. Here. So H to one side, and then the B to the other side. Right? If I'm looking at B, how many alkenes have I added to B? You have a question, Cameron? Okay. How many alkenes have I added to B? 2, because I only have 1 hydrogen left, right? And I started out with 3 hydrogens on boron. So here I would have added 2 moles. Right, so the D, you can see now I have 3 groups attached. So this is 3 moles. So this is all 3 of your alkenes added. Right, C is just to throw you off, because that would have added 4. But you can't add 4 if you only started with 3 moles. You can't add 4 moles unless you add in additional alkenes. So the question is, which alkyl borane will result from 3 equivalents of 1 propene reacting with BH3 is going to be D, right? When you see 3 equivalents, that's basically the stoichiometry of 3-to-1. So 3 parts alkene to 1 part BH3, or 3 moles of alkene to 1 mole of BH3. All right, any questions about that? All right, number 2, it says choose the correct product for the following reaction. What type of reaction is that? That's the first question. You can't pick the product until you know what the reaction is. So if it's mercury acetate and water, followed by sodium borohydride, which is NaBH4, what type of reaction is that? This one should click right away.
Oxymercurylation.
Oxymercuration, which results in what? It's a way to turn alkenes into what? Alcohols. What is the regiochemistry for oxymercuration? Markovnikov. That means that the OH is going to be on the more substituted carbon in the alkene. Is that right? So these are my choices for. Can I rule out C and D right away? Neither one of those are alcohols, right? So I'll rule those out. Because oxymercuration is a way to make alcohols. And in essence, it's like adding water across the double bond, H to one side, OH to the other side. So my choices are A and B. Which one of those is more Markovnikov, has more Markovnikov regiochemistry? A. The OH is on the most substituted carbon in the double bond. Right, and then B, what if I wanted B? What could I use to get B? If I wanted that alcohol instead with anti-Markovnikov stereochemistry. Yep. Hydroboration, oxidation. So mercury, I gave you a mnemonic. Mercury is Markovnikov. Boron is anti-Markovnikov. So if I want the anti-Markovnikov product, if I want the anti-Markovnikov product, I use BH3. All right, that's the next question. True or false? Hydroboration occurs with Markovnikov regiochemistry. True or false? False, right? It occurs with anti-Markovnikov regiochemistry. All right, so the next one, number 4, what type of reaction is that? Anybody recognize this reagent? MCPBA? It's an epoxidation. Excellent. It does epoxidation, which is an epoxide is what? It's a cyclic ether. Is that right? A cyclic ether that you can take an alkene and generate an epoxide, which is that cyclic ether, using either MCPBA or hydrogen peroxide. So when it asks to choose the correct product from the arrows, that's just a mechanism. We already went over that. We've seen that already. So which one of those is the epoxide? That's the question. It's not A because A is protonated. And the product based on the arrows is not going to be protonated.
D.
Did I hear somebody say the answer?
D.
D. That's my epoxide. Right. C is impossible because hydrogen can't make more than one bond. And then B is not a product, that would be considered an intermediate if it occurred. And then A would also be considered an intermediate. So again, epoxide is a cyclic ether. Cyclic 3-membered ether. It's just like a cyclopropane, but instead of carbon at the bridge, there's an oxygen there. All right, any questions about anything? All right, we can answer number 5, right? Which class of compounds do ethers do? I'm sorry. Epoxides belong to? I got turkey brain, even though I didn't eat any turkey. Ethers. My generosity overflowing, just giving, wanting to just give instead of waiting for the answer. All right, what I want to do here, you can see these reactions are either oxymercuration or hydroboration followed by oxidation. So I want to pause, I'm gonna pause my recording. And I want to pause and let you work through each one of these. Let me pause the recording because it's gonna be a silence. I need a taker for the first reaction. I don't care who it is, we got 22 people logged in. I know
I
that,
could try it, but I don't know if I might make some mistakes though. So
that's okay. That's why we make the mistakes here. It's like practice. This is practice for the game, which is the test. So make all the mistakes you want. That's where we can correct it. Or you want to annotate it, or you just want to call it out to me like what to do.
I can annotate it.
All right, great. While he's doing the first one, I need somebody to be thinking about that second. And building up the courage to put it on the screen. Anybody but a dead body.
I can do the second one.
All right. We're waiting on the first one. Do I need to stop sharing? No, I don't think I need to stop sharing. Let me check the security, make sure you can annotate. Share screen, and yeah, it's on. Okay, I see you now. I see you. So again, when we're thinking about these reactions, we don't care about any other functional group. We don't care anything about that ring, methyl group hanging off of it. All we care about is the alkene. That's it. That's where the reaction is going to take place. All right. You are 75% home. That's the wrong carbon. These are your alkene carbons right here. All right, so that's where you want to put your functional groups. All right. But you had it, I know your intent was, so you had it with the right regiochemistry. Go ahead.
Is that supposed to be a double bond right there?
No, I'm just
Okay.
saying where your location is for your
Oh, okay.
functional group. Because initially you had it on the ring. Well, no, you can put that back. You have had that part right. You just need to put the alcohol in. Yes. So where's your OH going? Which carbon? Well, I highlighted in orange. One of those carbons is gonna have an OH. The other one's gonna have a H. So where's it going? You had it right. You just had it in the wrong location. Yes. Great. You can stop right there. You don't have to show the other where the hydrogen is because it's understood to be on the other carbon. Excellent. All right. Somebody already volunteered for number 2. Go ahead. I need a volunteer for number 4 too. Be strong. It's Monday.
I can't annotate, but you would add the OH group to the least substituted the most substituted carbon.
Okay, which one? On the right or on the left?
It'd be on the right.
Okay, great. I got you. Fill that in for you. You saying here. Like that, is that right? Right, so this was my alkene, and these are the same two carbons right here. I add an OH to one side and an H to the other side. Okay. Kind of sloppy. You ready, Cameron? You can actually write on my iPad. Special. All right, who's doing number 4? This is why we got to get back to fully in person, because this is how this would normally happen. We'd be working through this in groups for the whole time we were doing it. Okay. Great. Thank you. Anybody disagree with that? Why is the OH on the other side now?
It's anti-Markovnikov.
It's anti-Markovnikov. It's a different reaction, right? The first two were oxymercuration reactions, which have Markovnikov regiochemistry, and then the last two are hydroboration followed by oxidation, which have anti-Markovnikov regiochemistry. All right, who's doing number 4, the last one? You need a new person, a 4th volunteer. Anybody? Come on out of hibernation. Do we have a taker? Be like the old folks, you can volunteer or be voluntold. Pick, we need somebody to step up to the plate. We got 1 minute left, 2 minutes left. Going once. Going twice. All right, we're leaving. Did you have it? Let me see. Excellent. All right, we're stopping here. I gotta send you a barrage of videos tonight because I didn't want to send them over your break. But I will do that. And then we're gonna pick up Wednesday, we're gonna start